All right, for lesson 2, we're talking about the Earth's mantle, and the things you should be able to do is describe the properties and composition of the mantle, along with explaining what the moho is. All right, so the Earth's mantle is directly above the outer core. We've already talked about the inner and outer core. It extends to a depth of 2,900 kilometers below the crust. Again, the numbers that I have here is based upon below the crust. If you want to know including the crust, it's going to be more of a range just because the crust can vary. 80% of the volume is in the mantle, so it's going to be the thickest layer, and 68% of the mass is in the mantle. So we can pretty much say that it's over half of the Earth is composed in the mantle. The moho is a very thin layer between the crust and mantle. It's basically just that separation layer. The speed of the waves, so our seismic waves, increases due to a difference in density between the 32 and 64 kilometer deep. So somewhere in here, that's when we get that difference in how fast the seismic waves are moving. But we can see that very thin moho drawn in. The mantle is made mostly of the elements silicon, oxygen, iron, and magnesium. And we do know that there tends to be more iron in the upper mantle, so closer to the surface. The density, temperature, and pressure all increase with depth, just like the entire Earth. Temperature can be from 870 degrees closer to the crust up to 220 degrees closer to the outer core. The rock in the mantle flows like a thick liquid. So think of like a hot asphalt when they're pouring asphalt, when it's coming out of the truck to make a road, it kind of looks like it's pouring like a liquid. So think of it kind of like that. It has plasticity, and plasticity is when a solid has the ability to flow. We've got 3 parts of the mantle. We've got an upper mantle, we've got a middle mantle, and we have a lower mantle. So the upper mantle is from the crust to about 410 kilometers down. It's mostly solid. It's malleable. So malleable means it can be pounded. Lithosphere includes the crust. So the lithosphere is the crust and upper mantle. It goes from the crust to about 100 kilometers down. So it only contains part of that upper mantle. And 50 to 100 kilometers thick, and it's broken into tectonic plates. And we'll talk about the tectonic plates in a later unit. And we know there's at least 7 major plates. We'll get into that stuff later. The big thing right now is knowing that lithosphere, the crust and upper mantle, is what composes the lithosphere. And you can see that right here on this image. The upper mantle also includes the asthenosphere, which is from the 100 to the 410 kilometers. So it's the rest of that upper mantle part. It's 130 to 160 kilometers thick. It's denser and weaker than the layer beneath the lithosphere. The temperature and pressure are so high that rocks are semi-molten. So they're not melted yet. They don't get melted until they get down to that outer core, but they're somewhat molten. And they also have plasticity, which flows easily. It's more ductile than the lithosphere and lower mantle. And ductility is the ability to deform or stretch under stress. So like if something's pushing on it, it's more likely to move, stretch, so on and so forth. And the asthenosphere also contains the magma that erupts from volcanoes. So the asthenosphere is this orange layer over here. The middle mantle is our transition zone. So this is where our characteristics are going to start changing a little bit more. Their radical transformations occur here, but not melting. The crystalline structure changes and becomes more dense. So it's going to be pressed together more. Since there's more pressure, it's going to start pressing together more. It does prevent exchanges between the upper and lower mantle. So it's kind of just a layer that's going to keep the asthenosphere separate from the lower mantle. So we're going to see more and more differences as we get further down. And there's a lot of water present. It's not present as water, but the particles that make up water are present. And the mantle is thought to include just as much water as there is on Earth, if not maybe even more. The lower mantle is from 660 kilometers to 2,700 kilometers. So that's this yellowish region. It's hotter and denser than the upper mantle and the transition zone. It's less ductile than the upper mantle, so it's not going to be quite as flexible. The intense pressure keeps this layer solid. And then beneath the lower mantle, there's a shallow region. So there's going to be like a shallow region below this that separates the liquid from the lower mantle. We're not going to get too much into the depths of that. But the main thing to understand with the mantle is that your characteristics are shifting as you go down. Convection currents are also present in the mantle. These are extremely important when we start talking about tectonic plates. Conduction. So conduction is when heat transfers from warmer objects to cooler objects. And when you're thinking of conduction, I want you to be thinking about the heat from the core is transferring directly to the particles above it. So if you were to touch your the vent for your furnace, it's warm. Your hand is going to get warm by touching that. That's conduction. When you put a pot of water on the stove, the pan or the pot that you're using is going to warm up through conduction. It's going to transfer the heat. Convection, on the other hand, is movement of a fluid such that the hot, less dense material rises and cold, more dense material sinks. So the rule you want to remember is heat rises, cold falls. And it's going to create a current, a circular pattern. So because the materials that are touching down here, they're getting conduction to heat up here. But because those hot particles need to move, they're going to want to rise. As they get further away and closer to the surface, there's nothing there to keep them warm, so they start losing heat. And then because the movement of the heated particles down here, it's going to cause the cooler stuff to fall. So, and hot materials are less dense, which also encourages the rising, and cool particles are more dense, which encourages them to fall. So in the end, we end up getting movement like this. Now, convection, you can see like if you're boiling a pot of water, well, maybe not boiling, but if you're getting it heated up enough that you can see that current that forms. Convection is air movement in weather. And also the particles within the mantle move by convection. So this will be very important as we move forward. You will need to understand this process. Okay, so the floating crust is another concept. The mantle is much denser than the crust, so the solid rocky crust floats on the mantle. Just like oil floats on water. The crust would be like the oil, the water would be like the mantle, so you're going to have that crust that kind of just sits above it. Isostasy is the balancing of forces between the crust and mantle. Iso means equal. Stasis means standing still. So between the two of those, it's like the force is going to be equal between the two. The crust exerts a force downward on the mantle, and the mantle exerts a force upward on the crust. If the crust gains mass, it's going to end up kind of floating lower on the mantle. If the crust loses mass, it's going to float higher. So here's an image kind of showing, okay, we've got ice. It's going to push down on the mantle. Mantle's going to push back. So there's going to be that exchange of force. In Norway, as ice melts off countries, the crust got lighter and floated higher. So that's where it's kind of showing, here's the ice. As the ice goes away, the crust is going to end up sitting higher. Mississippi River deposits sediment in the Gulf. The Gulf gets heavier and drops. So then that would be kind of the opposite situation because the water would then be pushing down on the Gulf.